Hello, welcome to MAT 223 Engineering Mathematics class. In this lecture, we will learn separable equations. First of all, what is a separable equation? A first order differential equation dy dx is equal to fx comma y is called separable if this the forcing function f x comma y can be factorized as a product of two functions. What is special about these functions? First of all, the g function is only the function of x and h function is only the function of y. So it is to say f can be separated into two functions like the product, and the first function will be in terms of x and the second function will be in terms of y. This way we can separate x terms from the y terms as a product. Okay, so as an example, we have dy dx is equal to e to the x plus y times sine x. This is a separable equation because dy dx equals e to the x sine x times e to the y is the other way to write this equation. So this e to the x plus y is equal to e to the x times e to the y. So it means we can separate y terms from the x terms by putting them like e to the x times sine x times e to the y. So this is our g function and this is our h function. So we can separate this equation and we say this is a separable equation. On the other hand, we cannot separate this equation because if you consider e to the x plus sine x, no matter what you do, you cannot put this in the spot g of x times h of y. You can try and you'll see each time you try that you will always have terms with x and y all the time for any function like that, for any product like that. Okay, so next, an example, solve the differential equation. It is x plus 1 times dx plus y times dy is equal to 0. So we can rewrite this ODE as x plus 1 dx is equal to negative y dy. So negative y dy. So it's basically moving this term to the right hand side. Also, on the right hand side, all the terms involves only the parameters y. So as you can see here, the right hand side is consisting of only the y terms, and on the right hand side we have only the x terms. Okay, so we can integrate both sides now. If you do that, we will see this will happen, and x squared divided by 2 here, x squared divided by 2 plus x is equal to, also we have a constant of integration, and this is equal to negative y squared divided by 4. Okay, so now we say this is the implicit solution of the given ODE. Okay, so we what did we do that? So here, this is basically we separated x terms from y terms and then integrate both sides. When we do that, we will have some terms with x on the left hand side and function with respect to y on the right hand side, and this will give us an implicit solution for any given separable ODE. Okay, so we observe that if we can separate terms with different parameters from one another on the other side of the equation, integration immediately gives us an implicit relationship between x and y. This implicit form is the solution we seek for the ODE. Okay, so this is where we're saying what's really happening here. Now, well, we will see this process on another example. Solve this differential equation dy dx minus x squared y squared is equal to x squared. Okay, so we need to move this term to the right hand side. If you do that, we will see it is basically equal to x squared plus x squared y squared on the right hand side, and on the left hand side the derivative of y with respect to x. Okay, so we have x terms and y terms here. We need to separate them from one another. We can do that by grouping in x squared terms. So this will be x squared times 1 plus y squared. Then you see this is only the x term times x function of x and its product with a function of y. So this is what's really happening, and this is a separable equation. Okay, so now what's gonna happen next? We divide both sides. Okay, so we consider this as the right hand side, and this is the left hand side. We divide both sides by 1 plus y squared. Okay, so when we do that, we will end up with this term. Okay, so it is basically dividing both sides, that we will have x squared on the right hand side and some fraction times dy dx on the left hand side. Okay, now we need to integrate both sides with respect to x. Okay, so when we do that, we will have this integration here. So this will be 1 over 1 plus x y squared times dy dx, and dx for the integration equals x squared dx. Okay, now we need to do something about this term here, because we have dy dx times dx sort of term. So let's see what's really happening with this guy. This this can be rewritten as the prime notation, like dy dx is equal to basically the x derivative of y, right? So this is the prime notation, and times dx. This is a better way to see what's really happening. Okay, so if you remember this term from the integration with substitution, this was really dy, right? So the x derivative of y times dx is equal to dy. Okay, so this is something you can remember from your calculus class. And then substituting this term, so dy or dy dx dx in the integration, we will see this is basically dy. Okay, so we replace this term with a dy here. Okay, now let's see what's happening. Okay, so we basically have only the terms with y on the left hand side, and on the right hand side we have only the only terms with x. Okay, so this is integration. Then when we integrate, this will be the arctangent of y, right? The derivative of arctangent of y is equal to that term. So this means we basically have arctangent y on the left hand side. On the right hand side, this is a power function. So this will be x cubed divided by 3, x cubed divided by 3 plus some constant of integration. So this constant has to be there. Also, we could have put some other constant here on the left hand side, but at the end of the day, we will have a constant anyway. So there's some other constant here and constant there. The difference of constants is a constant, so we just put one constant on just one side. Okay, sorry. Taking tangent of both sides now, we'll see this will be tangent. So taking tangent of arctangent will give us the original input. So this will be y, and this will be equal to tangent x cubed divided by 3 plus c. So this is our solution. Okay, so this was also our solution. Actually, this is also our solution, but this was an implicit form. If you want to write your solution explicitly, you will have to do one more step and say, okay, y is equal to that. Okay, so this is our solution. Now, considering this example, let's figure out the algorithm for solutions. Given a separable ODE dy dx is equal to f of x comma y, we need to put this differential equation into this form. So we need to separate x terms from y terms on the right hand side. So we need to write it as g of x times h of y. This is the first step. And then in the second step, divide both sides by h of y. When we do that, 1 over h of y dy dx is equal to g of x. Okay, So next we need to integrate both sides with respect to x. Okay, when we do that, we are not putting the integral there, but we need to consider only the right hand side and see what's really happening there. So this is 1 over h of y times dy over dx. Okay, so remember this was dy already from the previous example, and we just replaced this with dy, and this means on the right hand side the problematic part is only the right hand side, because this is a function of x, so we can integrate this with respect to x, no problem with that. Only the problematic part was on the left hand side, but it is not really a problem because we know this term is basically dy. Okay, so on the right hand side we have this, sorry, on the left hand side we have this, and on the right hand side we have g of x dx integrated. Okay, so this is what's really happening. And then once we take the integrals on both sides, we need to solve the resulting equation for y if this is possible, because in some cases, in some implicit cases, we cannot solve for y, we cannot separate or eliminate other terms from y. So this is if possible. Okay, so let's see the process on an example. Solve dy dx is equal to 2x y minus 3. Okay, so we need to put the differential equation into this form, and it's already in that form because 2x times y minus 3 is already the product of x function of x, and function of g, function of y, sorry. Okay, so when we do that, we are done with the first step, and then we need to divide both sides by y minus 3. Okay, y minus 3, and then we will end up with this term, this differential equation here, and then we need to integrate both sides with respect to x. Okay, when we do that, on the right hand side we have 2x dx integrated, and on the left hand side we have 1 over y minus 3, 1 over y minus 3, and then dy dx, and I know it's dy, so I just skip that part and say this is dy. Okay, you can do that all the time, so you can always put dy there, skipping this dy dx times dx, and this will be basically equal to, that integration will be equal to ln y minus 3. Okay, ln y minus 3, and here we have x squared plus some constant on the right hand side. Okay, so this is our solution, but it's implicit solution. If you need to solve for y, which is possible in this case, we need to put both sides on e power, so e to the ln y minus 3 and e to the x squared plus c. When we do that, e to the ln will give us the inside ln, so input of the ln, so this will be y minus 3, and here we have e to the x squared plus c, e to the x squared plus c. Okay, so this is, here we have, if you consider this power and the sum of the sum on the power means the product of each individual term, so this will be e to the x squared times e to the c. Okay, so e to the x squared is already there, but we don't see e to the c there, but c here. This means if you do e to the c, so if you consider e to the c, it's another constant. Okay, e to the c, because c is constant, arbitrary constant, e to the c another arbitrary constant. So why not putting just c here, because this is at the end of the day just a constant. Okay, so whenever we do some sort of manipulations on c and end up with new constants depending on c, we always put c there instead of like e to the c. Okay, so this way we simplify the problem because it's already c. Now we have, then if you move 3 to the other side, we have y is equal to c times e to the x squared plus 3 is the solution for this problem. Okay, Next, we have another example. So in this particular example, we need to solve dy dx is equal to y squared minus 1. If you remember from the last lecture, this is an autonomous equation, right? Autonomous differential equation, first order. And for an autonomous differential equation, we could say that right hand side equals 0. We could set right hand side equals 0 and then solve for y. The solutions for y will give us the solutions for differential equation. So in this particular case, y is equal to 1 and y is equal to -1 are two equilibrium solutions. Okay, so we know that before solving this problem, y is equal to 1 and y is equal to -1 are two solutions of this problem. Okay, we put them on a side, and then we are moving on our separable equation discussion. So if you separate parameters and integrate with respect to x, then we will see dy over x squared minus 1 is equal to basically integration of dx. Okay, so now when we take the integral, we will see x plus c is on the left hand side because we have 1 here hidden, so it will be x plus c. And on the right hand side, if you integrate this with partial fraction, we will see 1 over y squared minus 1 can be rewritten as 1 over y minus 1 minus 1 half 1 over y plus 1. Okay, so this is a partial fractions. If you don't remember that, you need to refresh your memory by revisiting some calculus books or your lecture notes from last years. So when we when we separate this as a partial with its partial fractions, we will see this differential this integration can be rewritten as difference of these two integrations. Then here we have 1 half ln y minus 1 on the first term, and then on the first integration. In the second integration, we will have negative 1 half ln y plus 1. Okay, so this is what's really happening. If you multiply both sides by 2, because we have 2 in common for both terms, so we will have 2x plus c. This is supposed to be 2c, but 2c is another constant and still a constant, so we just put c there. This c and that c are not the same, but still a constant, arbitrary constant, so we can always do that. Okay, on the right hand side we have ln, because the difference of ln functions will be the ln of their division. So this will be ln y minus 1 divided by y plus 1. Okay, so again, if you consider this natural log function, this is, and if you take e power, or if you put them on e power for on the both sides, you will see y minus 1 divided by y plus 1 is equal to c times e to the 2x. Okay, so this is again c, because e to the c will be another constant c. Okay, so this will be e to this will be c. So in the last equation here, if you solve for y, this is pretty straightforward. If you multiply both sides by y plus 1, okay, and then y plus 1, then it will be y plus 1 times c e to the 2x, and then move 1 to this side, or to right hand side, and then y terms to the left hand side, and then divide both sides by the coefficient of the y terms, then you'll end up with this solution. Okay, so this is our general solution. Now our discussion with this problem is about to end. First of all, we need to check if we can really recover our equilibrium solutions using this general solution. First of all, if you substitute 0 for c, because this is just an arbitrary constant, if you do that, you will see this term will go away and this term will go away. 1 over 1 will be equal to 1. So this general solution can recover y of x equals 1. Okay, So one of the equilibrium solution is already there. For the other other one, y of x is equal to -1, we cannot obtain this by this general solution. You can see that by setting y is equal to -1 and trying to find some c. You'll see there is no such c which makes y is equal to -1. For this reason, this -1 is not included in this general solution. Okay, so this solution is a singular solution. This is a singular solution, and this solution has to be included in the set of all possible solutions. Okay, so if you give the solution set and say, okay, the set in which all the solutions live, all the solutions of this ODE lives, you need to include this. You need to include this general form, and also y is equal to -1. Okay, these two both has to be there. Okay, so that's all for this lecture. Thanks for listening and watching. Bye.